And last summer, I did a summer placement at UKAEA, which is the UK Atomic Energy Authority. And I was actually looking at an X-ray of a T-Rex tooth. And I had to, which had been X-rayed, and then you could build a 3D image using the X-rays. Well, I was always really fascinated by nature in particular. That's kind of where my curiosity started. I wanted to know what everything was called and how everything worked.
Hello everyone, welcome back to my YouTube channel. Thank you so much for stopping by. Today I have the wonderful guest Emily, and she's going to tell us everything amazing about her. So the first question that I'm going to ask her is for her to introduce herself, who she is, where she works, and just to tell us a little bit about what she does.
Okay, hi, I'm Emily Howling. I'm 21 years old, and so I'm a very early career physicist. And last summer, I did a summer placement at UKAEA, which is the UK Atomic Energy Authority. And starting in a couple of weeks, I'm going to be doing a year in industry at Diamond Light Source. And so I'm really passionate about physics, particularly about diversity in physics and getting more women into physics. Yeah, so that's me.
Fantastic, thank you. Could you talk us through your journey from GCSEs to A-levels to doing your degree and then to finally getting your internship? I think it would be really useful, especially for girls who are going into physics or maths who are going into the A-levels now, to hear a bit more about your story, and maybe it's something that they could follow.
Well, I was always really fascinated by nature in particular. That's kind of where my curiosity started. I wanted to know what everything was called and how everything worked. And as I went through school, I just wanted to know deeper and deeper how these things worked, and that kind of led me to physics. And so from about 13, 14, I knew physics was what I wanted to do. And I was very privileged that no one really told me that I couldn't. So I did physics GCSE, I did physics A-level, got into uni. And then when I got to uni, I was quite surprised at the sort of atmosphere and culture that there was around women in physics in particular. Because obviously in STEM overall, women are underrepresented. But in physics, it's not great. It's about 21% of physics students are women. It's only really worse in engineering, which is about 12%. And so I was suddenly in this environment where I was kind of being quite underestimated, and people making comments that were kind of making me grimace. And so that's what really shook me up a little bit and made me think, okay, well, what can I do to make this better? And so that's how I got really involved in we have a women in physics group at uni.
Lovely.
And so I got really involved in that. I started working at open days as well. So I made sure that on open days I could like talk to the women applicants and talk to them about how to feel confident as a woman in physics, and try and advertise that we do have a women in physics group and encourage them. And so I got a bit of experience at kind of science communication, working on open days and science festivals. And I did do a small placement as well whilst I was in sixth form college. I did just 4 or 5 weeks at Manchester University Material Science Department. So it's not the physics department, but it was still a very physics-based placement. It was at the Henry Musley facility, and I was actually looking at an X-ray of a T-Rex tooth, and I had to, which had been X-rayed, and then you could build a 3D image using the X-rays. So I was building this 3D image of a T-Rex tooth and kind of looking at the structure inside it, and basically being a dinosaur dentist for a few weeks. And that was really important for me because I got a feel of what it's like being in a research facility. And that was also very helpful when I started applying for placements at the end of second year. And I applied for about 9 because you never know. It's always a little bit, none of them are ever a certain bet. So I applied for 9, got offers for a few of them, and decided to go to JET. And JET is the Joint European Tourists. That's the part of UKAEA that does fusion research. Shall I explain fusion?
Yes, could you also explain a little bit more about UKAEA, what they do, and then expand further into the area that you worked with them?
Okay, so they are they're a governmental organisation that
Yeah.
look after the whole of the kind of UK nuclear industry. So
Yes.
that means nuclear power, but also nuclear fusion. So
Right.
in nuclear power stations, energy is created through fission, which is when you get a big atom and you split it up into smaller atoms,
Yeah.
and energy is released. Whereas fusion is the opposite. You get small atoms, smash them together, and then they create a bigger atom, but a lot of energy is released.
Yeah.
And this is actually what powers the sun. So in the sun, protons, which are the nuclei of hydrogen atoms, there's like a chain of events that leads to them fusing together to make helium.
Yeah.
And that requires very, very high temperatures and pressures. And we can't create those pressures here on Earth because we don't have the whole weight of the sun bearing down on us. So we have to actually have higher temperatures than the sun to create fusion on Earth. We
Wow.
need 10 times hotter than the sun's core.
Wow.
And we also make the process a bit easier. Rather than using protons, starting with the very basic blocks, we actually use protons that have a few extra neutrons attached.
Okay.
So it's already closer to being helium. And these protons with extra neutrons attached are called deuterium, which is just one proton, one neutron, and tritium, which is one proton and two neutrons.
Mm.
So they smash together and make a helium nucleus, which is two protons, two neutrons, and then you get another neutron flying off.
Yeah.
And so this is a very clean way of producing energy because you don't get, there is still some radioactive elements to it, but it's a lot cleaner than nuclear fission because you don't get the same amount of radioactive waste. You just get helium, which is actually really useful, and we don't have enough of it. So it's a brilliant byproduct to get. But it is very difficult. You are trying to make a star on Earth and contain it and keep it under control and keep it at those high temperatures where fission can happen. And just collecting the energy off it and storing it is also a massive challenge. So we can do it, we can make it happen.
Yeah.
But we haven't yet managed to make it happen in a way where we get more energy out of it than we're putting in. So that's what we're working on. That's the end goal, is to have energy on the grid. But at the moment, we haven't quite reached that level of efficiency.
Okay, wow. So is that the area you're specifically working on, or is that the motto of the company as a whole?
So that was the specific area I was working in, because that's only a small part of what UKAEA does. It also
a
lot of other things. But yeah, JET is the name of the machine that does it at the moment.
Okay.
And that's what I was working. That's the group I was working with. I was actually working with the tritium science group, and I was. So there was an experiment being done to test materials for the wall of the machine, because they're about to build. Well, they are in the process of building an even bigger machine in the south of France called ITER. And JET, which is running at the moment, is like a mini version of ITER. So it's being used to test a lot of the things that are going to be implemented for ITER.
Right.
One of these things is the wall, because you can imagine the wall of this machine has to withstand very, very high temperatures. It has to be able to withstand those temperatures whilst not letting off any impurities that are going to go into the plasma and make it not work. Because the plasma. So when we heat up the deuterium and the tritium, it makes a super hot plasma, which is like a soup of these particles. And we hold it in place using magnets. So it's like a miniature star held in a donut shape. That's the shape of the machine, using magnets. And yeah, so the walls have to deal with a lot, basically. And so we need to find the best materials for that. And so my supervisor had an experiment where he fired a plasma beam, which is very similar to the plasma in the reactor, onto different materials, and you can see how damaged they were. You put materials in that were already damaged and see how they interact with the plasma. And so my very specific role was designing a piece of kit that would look at the plasma source and tell you exactly what was in it, so you knew how similar it was to the plasma that's going to be in the machine, because there's no point doing the test if the situations aren't going to be comparable. And so to do that, I was designing something called a mass spectrometer, which you can do it one of two ways. You either set all the particles off with the same energy and see how quickly they arrive at a point, which is called a time of flight mass spectrometer, or you do it where you have a magnetic field that deflects the particles, because if the particles have a charge, then they will go in a circular path in a magnetic field, if it's a kind of continuous magnetic field. And so you can see by the different amounts that they're deflected what their charge to mass ratio is, and so then you can work out which particles there are in which proportions.
Wow.
And so that was my very, very specific part of an experiment which was related to the bigger experiment, which is part of the whole picture of fusion.
Wow. So what is your job role, your job title exactly?
So when I was at JET, it was summer placement student of the Tritium Science Group. And my kind of job role and pay was looked after by a company called Rulion, so like a contracting company. So I was basically a contractor for the summer. But it was the first time I'd ever been paid for doing physics research, and that felt so amazing. I remember that first week where I could see the money in my bank, and I was like, oh, I'm being paid to do physics. I'm a proper physicist now. This is so amazing. So that was a really good feeling.
Lovely. I've got a few more questions. So how did you find physics at university compared to physics at A level? And then the second part is, how did you find applying your physics knowledge to your internship?
Okay. I enjoyed physics at university a lot more than physics at A level. I mean, A levels are not a fun time for anyone, I don't think.
Yeah.
I found a lot of physics A level. It kind of has to encompass a lot of material science and engineering as well. So that's very interesting. A lot of the topics I was particularly interested in, like particle physics, we only touched on briefly. Whereas now I'm at uni, especially now I can choose which modules I want to do, it's very much more tailored to what I want to learn and what I'm interested in.
Yeah.
I found it different at uni as well, that a lot of the motivation is on you. It's up to you to motivate yourself to do this work and to push yourself. But don't be... I found also people were coming in at a lot of different levels. There were a lot of different people coming in, very different A-level grades. Some people had done further maths, some people hadn't. So a lot of the first year was kind of getting everyone up to the same level and building everyone's skills. So things like coding, I had never done any coding before I came to university. First week of labs, they were like, now go plot a graph on Python. And I was like, what's a Python? And so that was a bit daunting. I felt like everyone else knew what coding was. But very quickly you pick it up, and you're not the only one. I wasn't the only one that didn't know what to do, and you will be surprised how quickly you pick up these things. So I enjoyed university. It's a lot more self-driven, which is the advantage of you can pick what you like and you can pick what to do, but also you do have to be quite motivated and quite passionate about it. Sorry, what was your second part of that?
The second part of the question was, how did you find, like, were you able to apply what you learned at university within your internship? Did you find the stuff you learned at university useful, and how did you apply your knowledge at uni into your internship?
Definitely. So a lot of the mechanics of how particles move in a magnetic field was important. Also, the coding skills I picked up were very useful. A lot of what I was doing was writing code that simulated how these particles would behave in my machine that I was thinking up. But also, don't be afraid to apply for placements where you don't tick all the boxes of what they say you need to already know. I know there's been studies done between like men and women, and I'm sure like other groups as well, where men will apply for jobs where they feel like they've got about 20% of the requirements, but women will only apply for jobs where they've got most of the requirements.
Yeah.
Definitely don't be put off if you see, they say that you need to be able to code in Python. I've only ever done like a couple of graphs. I don't tick that box. And also, it's the soft skills as well. It's not just about your smarts. It's about how well motivated are you, how well organized are you, but also you need to have creative thinking. You need to have good problem solving skills and good communication as well, which I think is often overlooked, particularly in the sciences, as something that you need to have, because there's no point doing the science if you can't communicate it, if you can't share what you found. And also, especially as an early career physicist, it's very important at this point to be building your network and to be making those connections. And so being a good communicator, having social skills is also very important. So yes, I applied for my uni knowledge, but I didn't tick all the boxes when I applied for this placement. I didn't think I would get the placement. I turned up on the day and I was like, I'm just so happy to be here. I'm just going to soak it all in. Try and enjoy the interview, and then I've just had a great day, so I'm probably not going to get it, but that's all right. And then I got it and I was over the moon. So yeah, don't be afraid to shoot maybe slightly above where you think you are, and you will have skills that you don't realize you have, because a lot of the skills that are needed are those softer skills.
Wow, fantastic. Thank you so much. So the next question is, can you tell us a little bit more about the new role you're going into? What sort of stuff will you be doing? And tell us a bit more about the new company that you'll be working for.
Okay, so I'll be working at Diamond Light Source, which is a really interesting facility. It's just outside of Oxford.
Yeah.
And it's an electron synchrotron. So it acts as a really powerful microscope or a really powerful X-ray machine. And it does this it's got a ring, a particle accelerator, and it accelerates electrons around to almost the speed of light. And they have this really cool property where when they go around a bend, they let off really, really intense radiation, which is synchrotron radiation. And it's this radiation that we use to do our experiments.
Yeah.
It's not like the Large Hadron Collider where we collide them. The electrons just keep going round and round and letting off radiation. And so there's lots of different experiments set up around the ring, and it's used. So Diamond Light Source is not in itself a kind of independent thing. People come to Diamond Light Source from universities, from industries to do research.
Okay.
And you have to pay to do it if you're in an industry, but if you have research which is very valuable, then you can get grants to go work there. So I know at the moment a lot of the research going on there is COVID-19 related.
Yeah.
They can use it as a giant microscope to look at the proteins in the virus, and it's used for everything from archaeology.
Yeah.
These scrolls that they didn't want to unravel because they would just crumble, and they could x-ray them with such precision that they could see where the ink was on the paper and then virtually unravel it and read it without having to actually damage the artifact.
Wow.
Yeah, so there's a lot of varied research that goes on there, like materials, archaeology, biology. And so what I will be doing is working with the beam diagnostics group. Okay. I'll be there for a year, and it's their job to make sure that the electrons in the beam are behaving the way they should, that everything is nicely working so that other people that are coming in can use the machine. And so the beam diagnostics group is a permanent group that are there.
Wow.
And so what I will be doing specifically is building a monitor to look at the spread of electrons in the beam.
Yeah.
Something called the beam halo, because the electrons don't just like nicely line up.
Yeah.
They have a little bit of a spread, and obviously this can affect your results, and also affect the way you control the beam, because if there's you want to keep the beam under control. You want to know where it is and how it's behaving. And so, I'll be building a monitor to look at this halo and look at the way the beam moves, the beam dynamics. And this is partly important because they're thinking about upgrading Diamond.
Yeah.
It will have a narrower beam pipe.
Yeah.
So we need to know, if we're going to have a narrow beam pipe, is that going to cause an issue with the way the electrons are spread out, and is that going to throw up any problems? So yeah, that's what I'll be doing. I'll be looking at the electrons, seeing what they're doing.
That's so exciting. I was really fascinated by being able to scan ancient scrolls and virtually unravel. I think that's amazing. That's so good. Wow, thank you. The last question I have is, what advice would you give girls and women who are looking to pursue a career in physics?
I think having a network and having mentors is very important.
Mm-hmm.
When I came to uni, I didn't know any physicists apart from like my physics teacher.
Yeah.
And it's very difficult for, you know, women and minorities, because they don't necessarily have relatable role models.
Yeah.
Because it's all very well and good looking up to Einstein, but I can't really relate to Einstein. I doubt we have that much in common. But so I spent a lot of time learning about historical women in physics.
Yeah.
I wrote 30 in my second year of university. I made 30 different posters about different women and minorities in physics, and put one up a week in the physics department. So that people would see these people and be able to relate to them, and also for the guys in the department to look at them and go, oh, so a physicist can look like that as well, and gain a bit more respect for people that weren't exactly like that. And so yeah, one of the most valuable things I got from my placement were the contacts, and I've got some really great friends and really great support network now, and that is very valuable, especially when you're feeling you're having a moment where you've lost your confidence, or you're not sure whether you're doing the right thing. Having other people that have been in the same situations that you can go to for advice is very important. And so that's what I would say. I would encourage people to go to conferences, go to events, find like-minded people. I went to the seminar early this year before everything stopped, which is a conference for LGBT people in STEM. And I met some really awesome people there, and it just had such a wonderful atmosphere, because it felt like everyone felt the sense of belonging and the sense of kind of no one was being judged, and everyone was just excited to be amongst a bunch of people passionate about STEM. Who didn't feel like they had to hide themselves at all. I'd say it's not about who you know in the sense of you have to know like really advanced physicists, really prestigious people. It's just about having a network of people who you trust and who can keep you going.
Fantastic. Thank you so much. That was very, very insightful. And that brings our STEM talks to an end. I'd like to say again, thank you to Emily for joining me and for allowing me to interview her, and for giving us an insightful view into the world of physics. And so thank you guys for watching this video. Make sure you like, subscribe, share, and comment, and I'll be back with another video. Bye.